Hello students, welcome to 60 out of 60 in KCET Chemistry 2025 series in just 200 days. Today we are going to discuss the last part of equilibrium chapter, which is like most important topics are covered in this lecture, that is ionization of acids and bases, buffer solutions and solubility product. Okay, you can join our WhatsApp channel, link is there in the description section. So with this you will be getting access to all our class notes, PDF notes, mock test and solutions. Okay, so yes, now let's get started. We are doing today the last part of this lecture, that is part 4, and in that we are going to discuss about ionizations of acids and bases. Okay, then we'll discuss about the buffer solutions, and lastly we'll be talking about solubility product. Okay, coming to year wise weightage, you can expect 1 to 2 questions from this particular chapter every year. Now if I see today's lecture, that is, first we'll be talking about this ionizations of acids and bases, and in that we have these many topics to cover, that is ionization constant of water, then we'll discuss about pH scale, ionization constant of weak acid, of weak bases, relation between Ka and Kb, di and polybasic acids, factors affecting acidic strength, common ion effect and salt hydrolysis. Okay, then we'll go for buffer solutions, and lastly we'll be doing the solubility product. Okay, now coming to the first thing, that is ionization of acids and bases. Okay, so the first here is, what do you mean by strong acid and bases? That means the acids or bases which dissociate completely. Okay, yesterday we discussed about strong and weak electrolytes, right? So those acids or bases which dissociate completely are called as strong acids and strong bases. Similarly, weak acids are those which dissociate partially. You can see the example of strong acids here and weak acids here. Okay, now one more very important thing, this is very important. Now see, stronger acids will have weak conjugate bases. Okay, now if you remember, if I have one HA, okay, and it is dissociating to give you H plus and A minus, this is an acid and this is conjugate base. Okay, now if the acid is weak, then its conjugate base will be stronger. If the acid is strong, then its conjugate base will be weak. Similarly for bases also, if we have a base like this, okay, and it produces, okay, now if a base is very strong, okay, then its conjugate acid will be weak, and if the base is weak, the conjugate base will be very strong. Okay, if the base is weak, the conjugate acid will be very strong. Okay, so that is clear here. Stronger acids have weak conjugated bases. Similarly, stronger bases have weak conjugated acids. Okay, fine. Now we'll go to ionic product of water. Now see, water, if you see, it can behave like this, that water can release one H plus and this water can accept this H plus to give you OH minus and H3O plus, right? Now if you see, water can behave both as an acid and a base, and that is why water is called as amphoteric, right? Now this water H2O, okay, is donating one H plus to give you OH minus, so this is behaving an acid. This is donating, this is accepting to become H3O plus, so this is behaving as a base. Okay, and at 298 Kelvin you will find that the product of H plus and OH minus concentration is 10 to the power of minus 14, and that is nothing but Kw. Okay, so we call that the ionic product of water, means the product of the ions of water is 10 to the power of minus 14. So this is 10 to the power of minus 7, this is also 10 to the power of minus 7. Clear? So we can say that Kw is what here? Kw is, one second, yeah. So Kw is the ionic product of water, means product of ions of water. Okay, ionic product of water. Now here Kw has H plus and OH minus. Okay, 10 to the power of minus 7, 10 to the power of minus 7, and it comes out to be 10 to the power of minus 14. So that is 10 to the power of minus 14. Clear? Next, talking about the pH scale. So we all know pH scale tells you about the acidic nature of a substance, right? So pH scale is from 0 to 14. I think all of you would have read it in your lower classes. 0 to 7 pH is acidic range and 7 to 14 is your basic range, right? Now pH is the measure of the amount of H plus ions present, okay? So the formula for pH is minus log of H plus concentration. pH is equal to minus log of H plus concentration. And now if you see this equation, right, I can derive this one and show you. Now if you see here, let me write down this one. This Kw is what? Ionic product of water. Okay. Now if you see this one, H plus into OH minus is equal to 10 to the power of minus 14. Now if I take negative log on the both sides, right, minus log of H plus into OH minus is equal to minus log of 10 to the power of minus 14. Okay. Now if I take multiply this one, so you know log of A into B is equal to log A plus log B, right? So we have now minus log of A into B, so I can write this one minus log of H plus, okay, plus minus log of OH minus, okay, is equal to minus log of 10 to the power of minus 14. Okay, so minus log of H plus is pH, minus log of OH minus is POH, right? Minus log of 10 to the power of minus 14 is equal to 14. Okay, so that is the relation, and this one, okay, this is called as your pKw. So pKw is equal to pH plus POH is equal to 14. This relation is very, very important. So if you know the pH value, you can calculate the POH value by just subtracting it from 14. Okay, or if you know POH value, you can calculate pH value. Okay, so this relation you must remember, this formula you need to remember. Okay, fine. Now we'll go to ionization constant of weak acids. Now see, any weak acid, suppose Ha is there, when you keep it in water, it takes H3O plus and A minus, right? Now this is a weak acid, so that means what? It will not dissociate completely, so that is why we have a equilibrium symbol here. Now what we can do is, we can consider let at time is equal to 0. The initial concentration of acid is C, this one is 0, this one is 0, okay? Now at T equal to equilibrium, when the reaction has already attained equilibrium, at that time some amount of Ha will dissociate, right? Now there is something term called as alpha. What is alpha? Extent of dissociation. Okay, now what means, if you have 1 mole of Ha, okay, from that alpha mole has dissociated. Okay, alpha tells you the amount, or alpha tells you the amount of acid that has dissociated from 1 mole of Ha. Okay, so now you see, suppose from 1 mole alpha mole has dissociated, but we have Ha how many moles? C moles, right? So from C moles, C alpha mole will dissociate, right? So now I can say that at T equal to equilibrium, I have C minus C alpha, where C alpha is the amount that has dissociated, right? Then if 1 mole is dissociating, we'll get C alpha of H3O plus and C alpha of A minus, right? How much is dissociating, that much amount will form here. Now if I write the equilibrium constant formula, okay, product concentration H3O plus into product concentration divided by this one, right? I'll write K equilibrium here. Okay, water is a solvent, so we are not taking this one. Now if I multiply this one here, okay, so what I will get, if I put this value, so I'll get C alpha into C alpha divided by C into 1 minus alpha. right? Now this equilibrium is called as Ka, because it is the equilibrium of acid dissociation, right? So now if I see here, we will get C alpha square by 1 minus alpha. Okay, so that is the value of Ka. Clear? So Ka is equal to C alpha square by 1 minus alpha. Got it? This is your acid dissociation constant. Okay, now talking about the alpha, as I told you, alpha is the extent of dissociation. Okay, so this Ka is your acid dissociation constant. So I can write here what is Ka. Ka is acid dissociation, okay, acid dissociation constant. First thing. Next, how can you predict the strength of an acid using Ka? So here also one very important thing you should know, that if Ka is more, okay, then it is a stronger acid. Okay, so what is it? If Ka value is high, that implies it is a strong acid. Okay, more is the Ka value, stronger is the acid. If Ka value is less, it is a weaker acid. Clear? This part. Okay, now we'll go to, okay, now here I have some formula to discuss, so I'll erase this. I have just derived this one, right? You have already seen. I hope all of you have noted down. So we will get this formula for Ka. Now this, how we calculate pH value, right? pH is equal to minus log of H plus. Similarly, you can calculate pKa also, which is minus log of Ka. So here, if Ka value is more, it is a strong acid, but if pKa value is less, then it is a strong acid. Okay, this is very, very important, and we generally get confused here, because you can see negative log of Ka is here. If this Ka value is very high, then this one will be very less value because it is negative. So pKa value will decrease. So if Ka is for an acid is very high, then it is a strong acid, and if pKa value is very low, then it is a strong acid. Okay. Coming to, similarly, we can discuss for your bases also. So at T equal to 0, the concentration was 0, 0, and at T, when it is, the reaction is at equilibrium, it is C minus C alpha and C alpha. Now Kb value will be what? C alpha into C alpha by C into 1 minus alpha. So that we will get here, right? So that will be Kb will be C alpha square by 1 minus alpha, and Pkb is equal to minus log of Kb. Here also same thing. If Kb value is very high, then it implies that it is a strong base, right? And if pKb value is low, then it implies that it is a strong base. Okay, so these two things you should remember. Ka value if is high, then strong acid. pKa value low, then strong acid. pKb value low, strong base. Kb value high, strong base. Okay, fine. Now we'll go to something that is relation between your Ka and Kb. Okay, so this also you should remember, what is the relation between Ka and Kb. So Ka into Kb will be equal to Kw. Okay, Ka into Kb is equal to Kw. Okay, so that is the relation that you should know. Next is, I hope all of you are writing all these formulas. Okay, please note down all these formulas. Next, there is one more thing. If you see, we just take negative logarithm on all the sides, then we will get Pkb plus Pka is equal to Pkw. So till now, what all formulas we have seen about pH? So first one we got is H plus concentration into OH minus concentration is equal to 10 to the power of minus 14. Same we got pH plus POH is equal to Pkw. That is one thing. Next, for H plus, it is Ka into Kb is equal to Kw. Okay, and another we got here is Pka plus Pkb is equal to again Pkw. So that is 14. Okay, clear? Next, let us see the next one, that is polyprotic acid and polyprotic base. Okay, now see, some of the acids like oxalic acid, sulfuric acid, phosphoric acid have more than one ionizable proton per molecule of the acid. Such acids are known as polybasic or polyprotic acids. Now, as you say, if one of the acid can have more than one H plus, it can donate more than one H plus. For example, H2SO4. First it will donate one H plus, then it can donate another H plus. Such type of acids are called as polybasic acids. Okay, so remember, polybasic acids are those acids which can donate more than one H plus. Similarly, there will be bases. Okay, what do you mean by polyacidic bases? Polyacidic bases means which can donate more than one OH minus. Clear? Polyprotic acid are those acids which can, or polybasic acids are those acids which can donate more than one H plus. You can see the name has confusion here. If an acid can donate more than H plus, we call it polybasic acid. If a base can donate more than one OH minus, we call it polyacidic base. Okay. Now, suppose H2X is donating H plus and HX minus, and in the next class HX minus will donate H plus and X2 minus, right? So, here suppose equilibrium is Ka1 and here it is Ka2. Okay. So, now if you see, you can certain examples, you can see that I have taken sulfurous acid, okay, sulfuric acid, H2SO4. You can see this Ka1 value is very large, then Ka2 value is less. So, always you will find that Ka1 value is greater than Ka2 value. Now, what is the reason for that? The reason here is it is more difficult to remove a positively charged proton from a negatively ion due to the electrostatic forces. So, you can see here, once this was a neutral species, right? You removed one proton, then you got a negative species, that is HX minus. So, this negative species will attract this positive H plus or positive proton more tightly, right? So, that is why removing a proton from a negatively charged species is very difficult. It is not an easy process. So, this one is a weak acid because it will not be able to give H plus easily. Now, because it is a weak acid, then the Ka value will be less. So, that is why Ka1 will be greater than Ka2. You can see these values here. Okay. Fine. Now, we will go to the next thing, that is factors affecting the strength of an acid. So, there are two factors that is affecting. One is your strength of HA bond and another is the polarity of HA bond. Okay. So, when you see the acids along a group, the strength of HA acids will be considered. Now, for example, so this factor is predominant when same group acids are considered. So, if you see HF, HBr, HCl and HI, right? So, H is a small atom, I is a big atom, right? So, what happens due to this? This is a very poor overlapping, right? Poor overlapping means the bond is very weak, right? The size is small and hydrogen size is very small. Ionic size is like iodine size is very big. That is why there is a poor overlapping and this bond is very weak. So, if it is a weak bond, it is easy to remove H plus from there, right? So, that is why easily H plus can come out. It can easily give you H plus. So, it is a strong acid. Okay. So, this strength of the HA bond or HX bond should be considered along the group. Okay. So, this is the order here. Now, but polarity of the bond means, suppose HA is there, polarity of the bond depends on the electronegativity. Electronegativity difference between H and A. Polarity of the bond is the electronegativity difference between H and A. Okay. So, here what happens, the electronegativity difference, if it is more, then the bond will be more polarized and it can break easily. So, this factor is more important along the period. Okay. So, now if you see along the same period, the acids are, for example, if you see CH4, NH3, water and HF, right. So, here you see the electronegativity, carbon, nitrogen, oxygen and fluorine. the polarity of the bond is increasing, so that is why the acidity will also increase. Okay. Next very important thing is your common ion effect. So here I'll tell you what is common ion effect. Now let us consider, for this you should know Le-Chatterley principle that we have already discussed in the last class. Now see, suppose I have an acid HA, okay, and it is a weak acid H plus and A minus, okay. Now I added something so that this A minus concentration, I added some extra A minus to this solution, okay. Then what will happen? Because if you remember, the concentration of the product increases, then the reaction will try to decrease the concentration of A. To decrease the concentration of A, reaction will go in backward direction, right? So if the backward direction is going, that means I can say that the dissociation has decreased, right? Dissociation has decreased because more HA is forming than dissociating to H plus and A minus. So that is nothing but your common ion effect. So you can see it can be defined as a shift in the equilibrium on adding a substance that provides more of an ionic species already present in the dissociation equilibrium, okay. So when you have already the same ion, if you add it, okay, so if you add the same ion, the concentration of the ion decreases, then followed by Le-Chatterley principle, the reaction shifts in the backward direction, and this is what is called as common ion effect. Due to this common ion present, right, this effect is shown, and due to which what happens, the dissociation is reduced. Clear? Okay, now let us go to the next one, that is hydrolysis of salt and the pH of their solutions. Okay, so now what happens, generally when salts are there, okay, if you put them in water, they will dissociate to give you cations and anions, right? So these cations and anions react with water. The cation can react, or anion can react, or both can react, or both of them cannot react. There are 4 possibilities I'll discuss. So when these cations and anions react with water, we call it hydrolysis, okay. So interactions of cations or anions or both of the salts is called as hydrolysis. Interaction of both with water, okay. Now cations of strong bases and anions of strong acids simply get hydrated but do not hydrolyze, and hence the pH is 7. Okay, we will discuss this in detail. Now let us take one example of a strong acid and a strong base, okay. Sorry, we will come back to this. Suppose I have second NaCl, right. NaCl is a salt of strong acid and strong base, right. Now what happens when you put them in water? It will dissociate to give you Na plus and Cl minus, right. So one second, if I have one second, okay, so now if you see, I have this one NaCl, okay, plus water. So what I'll get? Na plus Cl minus, right, and from this water also there will be ion form. What will be that ions formed? H plus and OH minus, right. Now what happens, this Na plus can again combine with OH minus, H plus can also combine with Cl minus. So what I will be getting here? NaOH, and I will getting HCl, right. But if you know, these are what? Strong base, and this is a strong acid. Strong base and strong acid means complete dissociation. So again they will dissociate to give you Na plus and OH minus. This one will again dissociate to give you H plus and Cl minus, right. So that is why they cannot react with water, okay, because they, again once they react, again they will dissociate. So the salts of strong acid and strong base do not react with water. What they can do? They can only get hydrolyzed by, they can also only get solvated by water. Means the water molecules can just surround them, but the water molecules cannot react with them, okay. So that is why it is told that the cations of strong bases and anions of strong acids simply get hydrated but do not hydrolyze. So the pH solution, the pH of such salt solution will be 7. Clear? Now we will go to the next case, that is weak acid and strong base, okay. So Now let us take the example of a weak acid and strong base. Once I take this example, it will be more clear. So I can take a salt of CH3COONA. Okay, if you think this salt is made up of CH3COH and NaOH, right, a weak acid and a strong base. Now if I keep this in water, okay, CH3COONA, if I dissolve it in water, so I get the ions, that is CH3COO minus, right, then I get Na plus, then from the water I get H plus and OH minus, right. Now what will happen, because these two can again react to give you, CH3COOH, okay, then in this we have Na plus and OH minus, right. Now you see this one, these two will not remain as NaOH because it is a strong base. In the aqueous medium it will dissociate, but this one will remain as a weak acid CH3COH, because you know this is a weak acid and it does not dissociate completely. So in the medium, what is there? In the medium we are left with OH minus. So these type of salt solution will be basic in nature. The salt solution of a weak acid and strong base will be basic in nature, and the pH here will be greater than 7. Okay, now what is the exact formula to calculate the pH? So the pH formula calculation is pH is equal to 7 plus half pKa. What is this pKa? The acid dissociation constant of this weak acid, plus half of log C. So whatever salt concentration you have taken, that is log C. 7 plus half pKa plus half log C. Now let us consider another example of a salt of strong acid and weak base. So let me take one example, that is NH4Cl, right. It is made up of a weak base, that is NH4OH, and a strong acid HCl. So now if this one is taken in water, okay, and you put water in that, right, so this is NH4Cl, sorry, so we have here NH4Cl. Now how will it dissociate? You will get NH4 plus, okay, then you will get Cl minus, you will get OH minus, and you will get H plus, right. Now what will happen? These two will combine, right, these two will combine to give you NH4OH. Now because it is a weak acid, it will not dissociate, so in the solution we are having NH4OH, Cl minus and H plus, right. So because of this H plus present in the medium, the solution becomes acidic. So these type of salt of strong acid and weak base are acidic in nature, right. If it is acidic in nature, the pH value will be less than 7, okay. But there is a formula to calculate the exact pH value, that is pH is equal to 7 plus half 7 minus half pKb minus half log C. 7 minus half pKb minus half log C, okay. So how will you remember? See, if it is a weak acid and strong base, base is what? Strong, so the medium will be basic. If it is a strong acid and weak base, so medium strong is acid, so it will be an acidic salt, acidic solution. Now remember, for acid it is always plus, and for base it is minus. For formula I am telling. So 7 plus half of pKa, okay, weak acid, that see Ka and Kb, the dissociation constants are always for weak acid and weak base. You cannot find a Ka for a strong acid, okay. So generally Ka dissociation constant are for weak acids. So this here a weak acid is there, so in the formula I will get a Ka. So 7 plus half pKa plus half log C. Now here we have weak base, so the formula will be 7 minus half pKb minus half log C, okay. Now we will go to the third category of salt, that is weak acid and weak base. So here if you see, I will take a salt like okay, CH3COO minus and NH4 plus, right. This is made up of CH3COH and NH4OH, a weak acid and a weak base. So now if I put water in that, okay, so I will get CH3COO minus plus NH4 plus H plus and OH minus, right. Now both of this will combine to give you CH3COOH plus NH4OH, right? So in this, what is happening, we are both having acid and a weak base in the medium. There is no H plus, there is no OH minus, but we have a weak acid and a weak base. So in this type of salt, if you want to calculate the pH, it is 7 plus half pKa minus half pKb. I told you with Ka it is always positive, with Kb it is always negative. Okay, so I hope this is clear. Let us summarize first of all. Strong acid and strong base, what will happen? Do not hydrolyze. Okay. Next, strong acid and weak base. Remember, strong acid means the solution will be acidic in nature and pH will be less than 7. Exact formula of pH. Now see, here it is a weak base, so Kb will be used, and with Kb it is always minus. So 7 minus half pKb minus half log C. Next we have weak acid plus strong base, right? Weak acid plus strong base, if you are having, this is a strong base, so that means the solution will be basic in nature and the pH will be more than 7, right? And if it is, so what is the value of pH? Now if you see it is a weak acid, so we will use pKa value. Weak acid means Ka will come, and with Ka it is always positive. So I'll get 7 plus half pKa, right, plus half of log C. Now if I take weak acid and weak base, okay, in that case what will happen? The pH value formula will be 7 minus half. So I'll write 7 plus half pKa minus half of pKb. This is the entire summary of the salt hydrolysis. Clear? Let us move forward. Now we'll go to buffer solutions. Okay, so now you see the solutions which resist the change in the pH on dilution or with the addition of small amount of acids or bases are called as buffer solution. So certain solutions are there. Okay, so if you add acid to it, the pH should decrease, but to certain extent they can resist this change. Similarly, there are certain solutions, if you add OH minus to that, right? So if you add OH minus, what should happen? The pH should increase, right? But yes, again, because there is pH will not increase, it will resist the change in the pH. Certain solutions are called as buffer solutions. Now buffer solutions are of two types, acidic buffer and basic buffer. Okay, so acidic buffer will be made up of weak acid and a salt of weak acid and strong base. Remember, this is very important. Acidic buffer will be made up of weak acid is there, so weak acid, and a salt of what? The same weak acid with a strong base. For example, I'll tell you, see, CH3CONa plus CH3COH. Now see, CH3COH is a weak acid here, right? It is a weak acid, and CH3COONa is a salt of this weak acid and another strong base, that is NaOH. Right? Similarly, we'll have basic, and its pH will be less than 7 because it is an acidic buffer. Now if you have basic buffer will be made up of what? It's the same thing, you can compare weak acid, here it will be weak base, and the salt of the weak base with a strong acid. Now here if I take one example, NH4OH, it is a weak acid, sorry, it is a weak base, NH4OH. So I will take a salt of this weak base with a strong acid. So NH4OH plus HCl, I'll get NH4Cl. So a salt and a base, and here a salt and an acid. Salt and base will give you basic buffer, salt and acid will give you acidic buffer. The acid should be weak in basic buffer, the base should be weak. Okay, and because it is basic buffer, pH will be greater than 7. Now how to calculate the exact value of pH? So here to calculate pH, it is 7 plus, okay, pH is equal to not 7, pKa, because it is an acid, right? Here we have weak acid, so pKa plus log of salt concentration divided by acid concentration. Okay, pH is equal to pKa plus log of salt concentration by acid concentration. And if I want to calculate pOH here for basic buffer, it will be pKb plus log of, one second, the same thing, pKb plus log of salt concentration by base concentration. Okay, salt concentration by base concentration. Okay, so these are the formulas for the buffer. So buffer is what? Something which can resist the change in pH. Buffer are of how many types? Two types: acidic buffer, basic buffer. Acidic buffer is a weak acid and a salt of weak acid plus strong base. Basic buffer, weak base plus salt of weak base and strong acid, right? Example here, CH3COONA plus CH3COH, and here for basic buffer, NH4OH plus NH4Cl, right? Next, acidic buffer pH less than 7, basic buffer pH greater than 7. Okay, fine. Then you have the formula to calculate pH, that is pKa plus log of salt plus by acid, and for pOH it is pKb plus log of salt by base. Now these equations, okay, to calculate the pH and pOH, this is called as Henderson equation. Okay, clear? Fine. Now we will go to something called as solubility product. Okay, so now see, what do you mean by solubility? The amount of solute dissolved in a particular solvent. The solubility depends on two factors, that is lattice energy and solvation enthalpy. Okay, and generally for a solid or for a substance to get dissolved in a solvent, the lattice energy, okay, for a salt to be able to dissolve in a particular solvent, its solvation enthalpy must be greater than the lattice enthalpy. Okay, so lattice enthalpy is the energy required to break the ions, to break or separate the ions. Okay, and solvation enthalpy is what? It is the energy released when the ions get solvated. Okay, so now here you can see the example. If it is we call something soluble if the solubility is more than 0.1 molar. Okay, and if it is less than between 0.1 to 0.01, we call slightly soluble, and if it is less than 0.01, then we call it sparingly soluble. Very less soluble is there. Okay, fine. Now something we'll talk about solubility product, very important. From here questions are asked. Now suppose you have a salt of AXBY type. Okay, now what will happen when it will dissociate? Okay, the solubility product can be calculated for sparingly soluble salts, means very less soluble. Okay, it is calculated for sparingly soluble salts. Now if you have AX plus BY, right, then we have like XA. Okay, let me take a simple example first, then we'll go to for this common example. For example, I have a salt like barium sulfate. Okay, I have a salt of barium sulfate. How will it dissociate? Ba2 plus SO4 2 minus, right? Now here the solubility is considered as S and this solubility is considered as S. Okay, now what is this solubility product? Solubility product is the product of the solubility of the ions. So it will be S into S. We will get S square. Okay, now for example, let me take calcium chloride. Okay, so how will this dissociate? Calcium 2 plus 2 Cl minus. Solubility here is S, here solubility is 2S. What is Ksp value? That is S, calcium solubility S, chloride solubility 2S, right? But here again it is 2, so 2 square will come, power of 2 will come, right? Just how you write the normal equilibrium formula, same like that. So here chlorine solubility is 2S, it is 2 times, so it will be taken as a power. So what I will get here? I will get 4S cube. Okay, next one, if I see, suppose Al2 SO4 whole 3, right? How will this dissociate? This will, let me write it like this. Suppose I have Al2 SO4 whole 3. So it will dissociate to give you 2Al 3 plus and 3 SO4 2 minus, right? So now this is 2S and this is 3S. So what is Ksp value? Ksp value is 2S and their power here is 2, so it is 2, and here it is 3S and it is 3. right? So what I'll get here? Here it is 3 3s are 9, 3s are 27, and it is 2 2s are 4, and here you see s square and s cube. So I'll get s5 into this one is 47108. Right? So this is how you calculate the solubility product, where S is tells you about the solubility. Okay. Now here if I have a general formula AXBY type salt, okay, then what is the Ksp value for this one? So if you have any AXBY type salt, okay, then the Ksp value will be equal to, okay, x into y, okay, into s to the power of x plus y. You can see the example here. What is there? 1 second. Yeah, x to the power of x, y to the power of y into s to the power of x plus y. Now you see this example. So this is x to the x is what? 2, right? And y is 3. So we have 2 to the power of 2, 2 to the power of 2, x to the power of x, that is 4. 3 to the power of 3, y to the power of y, so that is 27. Then s to the power of x plus y, s to the power of 2 plus 3, that is 5. Okay. So this is what you should remember, this formula about solubility product. Clear? Okay, so that is all about this today's lecture, and I hope today's lecture was with lot of formulas and you will be remembering these formulas. Note down these formulas. Ionic equilibrium, if you just do formulas and go, you can crack KCET very easily. We'll be discussing certain questions from these formulas. Okay, so the first one here is the homework question that I gave you yesterday. Which of the following is the conjugate acid of SO4 2-? So I told you, if you want to find conjugate acid, right, if you want to find conjugate acid, then what you have to do? Add H plus, right? You have to add H plus. So if I add H plus here, so what I'll get? HSO4 minus. Option number A is the correct answer here. Next question number 1. A weak acid with pKa value and a weak base with pKb are mixed in the equal proportions. pH of the resulting solution is. So this question is from salt hydrolysis. Okay, salt hydrolysis. In this, if you remember, we had 3 cases: strong acid, strong base, strong acid, weak base, weak acid, strong base, weak acid, weak base. So this is weak acid and weak base. So what was the pH formula there? 7 plus half pKa, right, minus half pKb. So if I substitute here 7 plus half, what is pKa value? 5.9 minus half pKb, that is 5.8. So if I solve this, I'll be getting around 7.05. Okay, the correct answer is option number D. You can check this calculation, you'll get the same answer. Okay. Next question number 2. Which among the following has the highest pH? So if you know, bases will have more pH definitely, acids will have less pH, right, because acids are strong acids, right, their pH value will be less. So we can eliminate these options because these are strong acids, their pH value will be very low. Now if you compare 0.1 m NaOH and 0.1, okay, so now you see here you have 0.1 m NaOH, right? So that means I can say the concentration of OH minus is 0.1 or 10 to the power of minus 1. Now from here, if I calculate POH, that is minus log of OH minus ions, right? So that is minus log of 10 to the power of minus 1. Now that I will get 1 here. This is POH value. Then what is pH value? If you remember, pH plus POH is 14. So that is 14 minus POH. So 14 minus 1, that is 13. Okay, this is done. So I got for option number B, the pH is 13. Now let us see option number D, where I have 1 molar OH minus. So what is OH minus concentration? Here 1 molar, like. So I can write POH here is minus log of OH minus concentration, and that is minus log of 1, and log 1 is 0, so I will get POH is 0. If POH is 0, then what is pH value? 14 minus 0, that is 14, right? So that means in option number B, the pH is 13 and here the pH is 14. So which is having the highest pH value? Option number D. Clear? Next question. Ka values for acids, okay, and are respectively this one. Which of the above acids produce the stronger conjugate base in the aqueous solution? Very, very interesting question. Let us note down the Ka values first. You have H2SO3 first, then you have HNO2, then you have CH3COOH, then you have HCN. Okay. Now, if you see these 1.3 into 10 to the power of minus 2, okay, then you have 4 into 10 to the power of minus 4, okay. Next you have 1.8 into 10 to the power of minus 5, and next you have 4 into 10 to the power of minus 10, okay. So these are what? These are the Ka values, and I told you, if you remember, Ka value, if it is high, then acid is what? Strong, right? Acid is also very strong acid. Next, if you remember one more concept, that weak acid will have what? Weak acid will have strong conjugate base. Today's lecture, first thing that we discussed was this one. Weak acid will have strong conjugate base. Now the question here is to find the strongest conjugate base. So if strongest conjugate base I have to find, then I need to search weak acid, and if I want weak acid, then the Ka value should be least, then acidity will be weak. So among this, you can see this Ka value is the least one. That means HCN is a weak acid, right? If HCN is a weak acid, its conjugate base will be the strongest one, right? So that is why option number D is the correct answer here. Okay, fine. Now let us go to the next question. Solubility of AgCl is least in. Okay, so while talking about solubility, we left one topic, that is common ion, which I already discussed in the acidic concept, right? So now, if you have taken AgCl, okay, how will it dissociate? To give you Ag plus and Cl minus. Now the same thing, if you have a solvent, okay, in the solvent, see, in the solvent, if you already have Cl minus ions, then what will happen? If more Cl minus will be present, then Lee-Chatterley principle will tell that the reaction will proceed in the backward direction and we will get solid AgCl. We will not be able to produce Cl minus ions, right? So that is why what happens here, you see in this one we have 0.1 molar NaCl, means I can say that there is 0.1 molar of Cl minus is already present. In pure water there is nothing is present, so it will be having maximum solubility. Then if you see barium chloride 0.1 molar, in each mole we are getting 2 moles of Cl2, so 0.1 means I have 0.2 moles of Cl minus. And similarly here I will get 0.3 moles of Cl minus. So more is the Cl minus, more will be the backward reaction, least will be the solubility. So that is why here the correct answer is option number D. The solubility is least here because of the more amount of common ion present in the solvent. Okay. Next is, which of the following salts will give a basic solution on hydrolysis? Very simple. If I want basic solution, right, the salt should be made up of what? Strong base plus weak acid, right? So you can see which of this will be strong as base and weak acid. Here it is NH4 is a weak base, here KOH and HCl both are strong, here it is a strong base, that is KOH, and a weak acid, that is H2CO3. So this one will give you a basic solution. Okay. Here it is also weak base and weak acid, so that will also not be given. Next question number 6. Which of the following salts with a concentration of 0.1 molar will give a basic solution? Again, you want basic solution, means we should have strong base. So you can see ammonium, 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 these are weak bases. Sodium acetate, sodium is a strong base, right? And acetate is a weak acid, so we will get a basic solution in option number D here. Okay. Next, okay, this is a homework question, but I'll be giving you a hint for this one. What is the pH of a solution obtained by mixing 10 ml of 0.1 HCl and 40 ml of 0.2 m H2SO4. So you are mixing HCl, okay, and H2SO4 in a container. Okay, so what you need to do, you need to calculate the pH of the resulting solution. So hint here is, first you need to calculate the H plus concentration in this present in HCl, then you need to calculate the H plus concentration present in H2SO4, then you need to add the total number of H plus that is present, and then you need to calculate the pH value. Okay, so try this question, or else I'll be solving it in the next class. So thank you students, and I know this lecture was little complicated with so many formulas, but please understand, in the next class we'll be doing so many numericals from this particular chapter, so that you can just clear all your concepts. So make sure that you revise these formulas and come for the next class. Thank you for watching, and please subscribe the channel for more such videos.